Let's pray and we'll get started. You ready, brother? Father, thank you for today and for these two men and for anybody who's going to watch this online. Just pray that you help me to make some of these complicated topics clear and understandable. Lord, help us to understand and to see something of your goodness, your glory, your good plan in creation. For our good and for your glory, we pray in Jesus' name. All right. So we are going to pick up where we left off for you last semester. Everybody else, you'll catch up where we're at. So the section we were going into is what's called VESPR, V-E-S-P-R. recording cut out, but I'm going to say this for everybody watching the recording, not for you guys. What we're doing is we're looking at shapes of molecules. We're going to begin with the VESPR theory. We started with just a formula and then drawing a loose dot structure. The next thing we're going to do is look at what these would actually look like. Start with hydrogen. So hydrogen has two atoms. They're bonded together, right? We have it drawn like this. The question is, does it actually look like this? Do I have just this isolated region of positive charge, isolated region of positive charge, and a strong negative charge in between? Or does it look something maybe quite a bit different than that? What about beryllium dihydride? So what we can do with something like this is you can imagine a central atom, and we're going to look at regions where electrons are adjacent to it, right? So I've got your hand is going to be the central atom. Hold up your hand, okay? How many regions of electron pairs do I have coming off of this? Two. So what you would do then is you take two of your balloons and you hold them. And these electrons, they want to be as far away from each other as they possibly can, right? So where are they going to be? What shape is this going to form? Yeah, it's going to look like that, right? Because if I put these as close as I can with my fingers, okay? As close as I can, they're bonding, right? I mean, the electrons are attracted to the central atom, but the truth is the electrons still want, I can try to hold them like this, but they're going to spring apart, right? Because they're repulsed by each other because of the same charge. So just this helps us to realize it doesn't look like that, right? It looks like this, right? Does that make sense? So this is what we call, where am I? I'm on the wrong one. This is what we call the VESPR theory. I'm going to give you some information here. Valence shell electron repulsion theory enables us to predict the molecular structure, including the approximate bond angles around a central atom. So for instance, if we're doing beryllium dihydride, what's the bond angle between these electrons and these electrons and the central atom?
That would be 90 degrees.
Well, I think that would be 90.
Oh.
It's going to be 180 degrees, right? So this theory, or if you're playing with balloons, allows you to predict the bond angles. It's very, very helpful. Let me read that again. It enables to predict the molecular structure, including approximate bond angles around a central atom of a molecule from an examination of the number of bonds and lone pairs of electrons in its Lewis structure. Notice this one does not have any lone pairs of electrons. So we do want to begin with the Lewis structure, but we don't stay there. VESPR model assumes that electron pairs in the valence shell of a central atom will adopt an arrangement that minimizes repulsions between these electron pairs by maximizing the distance between them. They want to get as far away as they can. The electrons in the valence shell of a central atom form either bonding pairs of electrons, located primarily between bonding atoms, or lone pairs. So let's do one that would show some lone pairs. Let's do oh my goodness, all of a sudden I'm just going, oh, I don't know anything at all. Let's do water. Okay, let's do H2O. So I've got oxygen, right? How many electrons total?
8.
8. 6 in its valence. I go 1, 2, 3, 4, 5, 6. Okay? So these are pairs of unbonded electrons. I'm going to form a bond here, and I'm going to form a bond here. Right? And so, with this, I don't just want, because we're representing pairs of electrons, whether they're bonded or unbonded, how many balloons am I going to need in my hand? 4. Okay, so do me a favor, get two of one color and two of another color, okay? So when I put these as tight as I can, if I just have three, look at what shape they fall into a plane, right? But as soon as I add a fourth one, three of them want to move down, if my hand would just get out of the way, right? But maybe I can do it better here. I can't. I can just take these, right? Take a look at the shape they make. This shape is called a tetrahedron. Okay? One kind of sticking up, and the other three kind of pointing down in another point. Right? So that's, and so what we do, we might look at this as, I've got oxygen in the middle. These are where the hydrogens are bonded. This is an unshared pair of electrons. This is another unshared pair of electrons. These unshared pair of electrons have an effect on the two hydrogens that are bonded, right? It repels them, pushes them away, so that the shape of water is not linear, right? This was linear, right? You had a central beryllium, and then you had two hydrogens, and it was linear. But the effect of these other electrons takes up space, actually even greater than if there was just a bond there. Well, let's keep reading here. The electrostatic repulsion of these electrons is reduced when the various regions of high electron density assume positions as far away from each other as possible. VESPR theory predicts the arrangement of electron pairs around each atom and, usually, the correct arrangement of atoms in a molecule. We should understand, however, that the theory only considers electron pair repulsions. Other interactions are not accounted for. All right. Let's build these. Okay. So BH3. So how many regions am I going to have? How many balloons do I need to pick up? Three. Okay. So take a look at what 3 is. What shape does it make?
Triangle.
Well, kind of. If I pulled it this way, it is, right? What if I hold it this way? Yeah. So this shape is just what we call planar or trigonal planar. Okay. Maybe we should start drawing these. It's probably a good time to draw what these look like. Marker. All right. This one looked like this, right? We just call that linear. This one looked like this. Right? We call that trigonal planar. This one, we already have a version of it. We did it up here. What do we call this? Tetrahedron. And you want to draw that?
I remember the tetra, no, the rest.
Okay. So one of them's going up. One of them's kind of coming out. So draw that better. I like how that came out. me draw it better. See how your boat draws it better. Let me draw it the way your boat is. Something like that. Okay. This shape. Now the next one.
How do you write it?
Oh, I'm so sorry. Okay. When I add another balloon, I'm going to add another level of repulsion. It's going to change things. Notice I get 3 of these in a plane, right? Well, it is what it is. Tear it up if I move it. These 2 reds are in a pole, or the red and the blue are in a pole together. They're 180 degrees away from each other. These other 3, they're 90 degrees away from one's in an axis here, the other 3 are in an axis here, okay? These 2 are 180 degrees away from each other. They're 90 degrees away from these, and these are all 360 divided by 3 is 120 degrees away from each other. So this shape is referred to as trigonal or trigonal bipyramidal. Let me write that part down first. Trigonal bipyramidal. Now, how on earth do you draw that? Well, you've got a lobe up, you've got a lobe down, and then essentially you have 3 lobes in this plane. Okay. That's a terrible drawing. Absolutely terrible. The idea is you're about 120 degrees away here. About 120 degrees away here. About 120 degrees away here. But between this one and these, you're 90 degrees away. Right? Yeah, that is just an awful drawing. I'm sorry. This is page 345 on your book if you want a really good drawing. Okay. It's called trigonal or trigonal bipyramidal. Idea is that you're forming 2 sets of pyramid shapes. All right. And then our last one here is kind of where we began. Now, you guys see my white ones?
It's on the floor.
Sure. So, begin with my tetrahedron. Add these white ones into it. Them as my, that was nice, you can see that clearly, right? The 2 white ones form an axis, right? And then these other 4 are, that's fun stuff right there. These other 4, I can do that all day. These other 4 are in a plane together, right? And so the 2 white ones are 180 degrees away from each other. These are no more than 90 away from each other, and these are 90 away from each other, right? Okay, so that one's a little easier. Okay. And this one is called just octahedral. Should have drawn some of these others for you. The bond angles here are 360, right, in a circle. So we got 3 of them in that circle. So how much is it? 360 degrees in a circle, right? We're in a plane. I got it divided in 3, so it's 120, right? And this is simply 180. This one's a little different. The tetrahedron is a weirdo. It's 109.5 between all of them. Show you how to, y'all do this. I'm going to do some other drawings for you real quick that you're going to need. Get rid of our water, or our H2 rather. Just do me a favor and just look up. This madness is a stick version of these. We're trying to create somehow a 3D rendering that's simple of what's happening here, because this is hard to actually draw. Linear is easy, they just form a line. Trigonal planar is easy, right? It's just, what's it, BMW or whatever that uses that?
Mercedes.
Mercedes, yeah, I'm poor. I didn't even grow up seeing those. Tetrahedral. So what's happening here is, is you've got one that's sticking up, right? And you've got one that's really coming towards you, and that's why they show this kind of big and thick like this and coming out, is because it's coming towards you. One's just hanging out on the side, and the other one's in the back. And so we just go like, hey, it's going away from me. And so anytime you see this big wedge, it's trying to show you, hey, this thing's coming towards you in the plane that we're trying to draw, and the dotted line's going away from you, and anything just solid is just, on the plane. So that's what this is supposed to represent. This. And if you go on to take like any other chemistry, certainly organic chemistry, this is the thing. You're going to draw this, and even in this, you're going to draw this over and over and over and over. You won't draw this so much, you won't draw this so much, because this is what carbon does. Right? This would be like methane, CH4, or carbon tetrachloride, or carbon tetrafluoride. It forms this shape. You draw this over and over and over again. Practice. Draw this a bunch of times right now and get comfortable with it, because you've got to be able to do it. And then here, just remember, we got 2 on an axis, and we got 3 in a plane, right? I mean, if I had built it well, I could have spun it like I did the other one. This one did good, this octahedral, right? So 2 on an axis and 4 in a plane, and we could just spin that joker. So that's what's going on. Now, of course, when you draw these in real life, let's not just draw them. Let's draw a real thing. Draw methane. Draw CH4. Okay? So you start with carbon as your central atom, right? And then I need some way of representing those. That's what my methane should look like. My little ones will be going nuts right now with these balloons. My oldest boy, Theodore, for his 2nd birthday, we got him a little trampoline with a bar that you jump on. And we covered it with like a blue thing, so you open it or whatever. And he loves balloons, so we blew up a bunch of balloons and just had him on the trampoline and everywhere else. It was 2 hours before he jumped on the trampoline because he was running around, and he called them boons. So for 2 hours he's just running around hitting them and yelling, boons, boom. They still love balloons. Crazy about it. There we go, that's trigonal bipyramidal right there. Got it. You do it.
Skinny.
Alright. Y'all ready to move on?
Yep.
Okay, good. My notes go. Yeah. So now we're going to talk about the difference between valence shell electron and electron pair geometry. So electron pair geometry versus molecular geometry. There's a little difference. I'm going to erase everything that we just did. If you need a picture, do it quick. Okay. All right. Here we go. Keep in mind, I just spent, what, 45 minutes on this? Something like that? So, it wasn't just because I like drawing and I like balloons. You got to know this. I did it in this way with the balloons and everything, so hopefully it becomes really concrete. You can take the balloons and practice, and people will make fun of you, but or they'll steal your balloons because people like balloons. But
Pop the balloons.
pop balloons, yeah. Depends on who it is. But you need to play with these enough that you know them, what they do, what they're like. I'm gonna show you one other trick for a tetrahedron. This is definitely something from like organic chemistry. So, if you ever take organic chemistry, it's it's just carbon. That's the whole thing, right? That's why they call it what they do. And so you're just dealing with carbon. You're trying to name things and imagine how things are and build it, and then you got to draw it on a piece of paper. But it's all just type stuff, and then you've got to be able to visualize it. And so,
That's her.
huh?
That's her. Visualization, how the carbons accommodate in the molecule. That's her.
It's hard, isn't it?
No doubt. So what they do is that thing that we did where we have this, you do that with your hands. Your fist becomes the central carbon, and then you have these three right here, and then this is the one sticking up. And then you can kind of rotate it, and you can imagine carbons, another thing. Just one more way to think of this. This is a tetra, 4, right? 1, 2, 3, 4, tetrahedral, okay? All right. Let's go on. So, electron pair geometry. Versus molecular structure. What does this want you to know? It says the electron pair geometry describes all regions where electrons are located. That's what we've been doing. Bonded as well as lone pairs. However, molecular structure describes the locations of atoms, not electrons. So, electron pair geometry, what it wants you to know is describes location of all electron pairs, right? Versus molecular structure describes location of atoms. We differentiate between these two situations by naming the geometry that includes all electron pairs, the electron pair geometry, and the one that does atoms, the molecular structure. The electron pair geometries will be the same as the molecular structures when there are no lone electron pairs around the central atom. But they will be different when there are lone pairs. The difference, these become different when there's a lone pair. Quite sure what note that was. You nailed it both times. So let's do boron trihydride. Okay, so BF3. For BF3, you got a central boron, right? And it's making 3 bonds, right?
Mm-hmm.
That's it. What shape is that?
Tetrahedral. No? This one.
Trigonal planar.
Trigonal planar. Yeah, it's just going to do this. Right?
Okay.
I did F. Put that back. 4. That's what it looks like as a molecule. If I'm worried about, well, where are the electron pairs? Well, it's going to look like this, right? also trigonal planar. But now if I do water, if I do water as a molecule, right? Let's start with water with its electron pair geometry, right? I've got a central oxygen. I've got it bonding with hydrogen. I've got it bonding with hydrogen. I've got it with an unbonded pair of electrons, right? I got it with another unbonded pair of electrons. What shape is that? Tetrahedral. But if I get rid of the unbonded electrons and all I draw is where the atoms are, what's that? That's called bent.
Or angular, right?
For the molecular structure.
Oh.
So the electron pair geometry of water is tetrahedral, but the molecular structure of water is bent. Okay? They're related. I can't accurately determine this without considering this. Because these electrons, if all this was an oxygen and 2 hydrogens and there was nothing else, then those hydrogens are going to do this, right? They're going to get as far away from each other as they can. But because I have unbonded electrons, all in all, I get 4 lobes where electrons are located, right? 2 of them where the hydrogens are, and 2 of them where unbonded electrons are. Well, for this one, I consider everything, right? This is here, that's what we did. But for this one, I can't consider these. I'm not going to pop them, but you get the idea. I just got to pretend they're not there, and then all of a sudden, all I've got is this. Okay, so they're related. They influence each other, but they're not the same. They are the same if I have no lone pairs, but as soon as I get a lone pair of electrons in there, it does change, or the 2 become different.
Like always the same shape, just you have pairs or not pairs, the electrons, right? It's like something like that.
Can you ask that one more time?
No. Like, is when you have a parallel, it's like half an atom, right? It's like half another molecule right over there.
Pair of electrons?
In the geometry, right? I don't know how to explain it.
I know it, and I'm having trouble even just with the...
Like when you are using the structure of geometry,
Okay.
that explain everything. It's like an example in water. It's like having 2 other atoms of hydrogen.
It has... let me take what you're saying, and I'm going to put it in mine, and you tell me if it's what you're saying. This is equivalent, shape-wise, to if I had this. Is that essentially what you asked? Yeah, exactly. Exactly, perfect. Okay, that's good. So they give the example of methane, which we just did there, and methane would have been great. Methane is going to have the same, this is methane with molecular structure. It's also methane with electron pair structure. But let's do, then they give ammonia. Ammonia is NH3. Let's do ammonia real quick, okay? So, NH3. How many regions of electrons do I have? If I did ammonia, NH3, right? It's 1, 2, 3, 4, 5, right? So don't forget to start with your. If you don't start with your Lewis dot, you can get yourself twisted pretty quick. But this shows me I've just got 4, right? That's all it is. Well, okay, that's not hard. That's it's going to be tetrahedral. I got 4 areas. So I got these 2 electrons. I've got a hydrogen coming to me here. I got another hydrogen here. I got a little hydrogen back, right? That's my electron pair geometry. It's tetrahedral. But now, and so maybe here's the trick for us all. Ready? If I want to do my molecular structure, just delete the dots. Okay, well, what is that now?
Upper order.
Goodness, I just lost my cat. There it is, right. It's trigonal pyramidal. This is called trigonal pyramidal. It forms a pyramid with only 3 sides, right? Or a triangular base. Ah, I stink. Forms that kind of thing, right? Okay. So trigonal pyramidal would be what that's called. They want you to know a few things that are super, super critical at this moment. They do matter. So I told you just a little while ago that in a tetrahedron, the bond angles are 109.5 degrees, right? So if I have methane, we do this. You draw methane, and we'll do ammonia. I know that all these bond angles are 106 or 109.5. All of them are, okay? They're equally repelling each other, but that's not always the case. When I have an unbonded pair of electrons, it actually takes up more volume and it has a greater repulsive force on the single bonded electrons, okay? And so this will be greater than 109.5, and these, consequently, because this angle here gets reduced, then the angle between any 2 of these gets reduced, okay? And so in something like this, you're probably going to get something more like something probably like 109 or even less. So we'll do, what is it, less than or equal to 109, right? Whereas this was 109.5, it's going to get shrunk out because this unbonded pair has a greater repulsive effect on everything else. It's crazy hot in here. What time are we on? What time are we at here?
150.
150, okay.
I have a question. What about the labs? We are going to do
That's with
labs.
you.
Okay.
That's with you. Okay. All right. What do they want you to know? Molecular structure of CH4 is shown. All right. According to VESPR theory, the terminal location of atoms are equivalent within the linear, trigonal planar, and tetrahedral electron pair geometries. It does not matter which X is replaced with a lone pair because the molecules can be rotated to convert positions. However, for trigonal by pyramid, here's what it's saying. Translate what I just read for me and for you. gonna go see if I can shut that stupid heater off. I'm getting killed right now. Be right back.
¿Qué dijo de los laboratorios que sí vamos a tener, cierto?
¿Cómo?
De los laboratorios que dijo.
Que como que no tienen un laboratorio acá, no hacemos como baldes pues.
O sea, solo tenemos clases instaladas.
Sí, hasta ahora hay 50 y nos vamos. Y creo que va a estar como un proyecto o algo para hacer como la...
The other room's at 67 degrees, and it's like 80 in here. It's crazy.
Boiling.
Remember how it was freezing last, in the summer? Yeah.
Yeah.
All right. All right. So if I do, and I do linear, right? And I've got one bonded. I've got one bonded pair right here, and I've got one over here that's unbonded. Okay. So this is what's kind of going on, right? Got a pair here, and I got a pair here. That's going to stay at 180 degrees, right? Because this is going to affect, equally. That's going to stay at 180. Not going to change. If I do a trigonal planar, it doesn't matter where I draw this, because this thing just rotates. It does not matter. I can envision them in any place. Okay. And either way, this is going to be a little greater than 120 degrees, right? And this is going to be a little less than 120 degrees. I can do the same thing with tetrahedral. It does not matter which one of these I do as my unbonded pair, because it can rotate equally freely, right? However, once you get up to these next two, it matters greatly, because you've got some of them that are in an axis, and you've got some of them that are in a plane. And which one is which really matters. So, I want you to take a look real quick, right? Ian, you with me? Stay with me. I want this to be my unbonded pair. If my unbonded pair is here, right? Then the angle between these and any other one is 90 degrees. If it's here, then it is 120. So it cannot be an axis. It cannot be on the axis. It must be in the plane, right? So let's shift that somehow, make it in the plane. Okay. So for trigonal bipyramidal, it must be in the plane, okay? Because remember, it's repelling more. That's all that's really saying. Trigonal bipyramidal electron pair geometries are two distinct expositions. An axial position. Okay. All right. theoretically, we can come up with 3 possible arrangements for the 3 bonds and 2 lone pairs for the ClF3 molecule. So let's do chlorine trifluoride. Okay. So this is one that has hybridized. ClF3. So we start with chlorine, right? Chlorine has 7, so 1, 2, 3, 4, 5, 6, 7.
Mm-hmm.
Right, so I'm going to do 1, 2, 3. All right, how many regions of electrons do I have?
5.
5, right? So that should be my trigonal bipyramidal. Now, let's see where it's going with this. It says, theoretically, we can come up with 3 possible arrangements for the 3 bonds and 2 lone pairs for the ClF3 molecule. The stable structure is the one that puts the lone pairs in equatorial positions, giving a T-shaped molecular structure. So what it's saying is...
It's bent, right?
Hmm?
It's bent.
It's actually going to be a T. It's like going to be,
Okay,
they're going to call it 90 degrees.
Oh,
So
Oh.
what you would have normally is you'd have Cl. I can put an F in an axis. I can put an F in an axis. I can put an F in a plane. I can put an unbonded pair in the plane, and I can put another unbonded pair in the plane, right? And so this allows these the most space to spread out, and these 2 are going to be perfect, 180 degrees from each other, right? More or less. And this guy is going to be as far away from each of these as he can, and so this is going to be pretty close to 90, 90, so we'd call this a T. All right. When a central atom has 2 lone pairs and 4 bonding regions, we have an octahedral electron geometry. The 2 lone pairs are on opposite sides of the octahedron, though, 180 degrees apart. So let's do what that one would look like. So you're going to have a situation like this. And say you want to put them here, you want to put them here, and everything else is on this plane. This is, now, the name of this shape, then, if we were to draw this, it looks like an X, right? But we don't call it an X. We call it a square planar. So we had a trigonal planar, I guess because of how you connect the dots, right? So, hence the name square planar. All right, they give you some rules. Write the Lewis structure of the molecule or the polyatomic ion. Count the number of regions of electron density. Single, triple, or double bond counts as 1 region of electron density. We didn't even do those yet at all. Do you want to do one with a double bond? See what it looks like?
Yeah.
Okay. Let's do do that. Okay. Or C, I guess it'd be CH2, but I'm trying to draw it where you can see it easier, right? So we'll go ahead and draw this one. Draw it first with an electron dot form. It must be Aaron at soccer balls. I'm going to look at it like this. How many regions of electron density do I have?
3.
3.
Mm-hmm.
Okay. So that's going to inform me of what my shape is, right? It's going to be, what's it called?
Trigonal planar.
Trigonal planar. That's good. Let's do one more of these. Let's do, you'll get this, right?
No, I don't.
You didn't get this?
No.
Okay. Okay. Let's start here. Start with carbon,
Yeah.
right? So how many valence electrons? 4.
4.
So we put each of those, right?
Yeah.
1, 2, 3, and 4,
Mm-hmm.
right? 2 of these are going to be bonded to hydrogen, right?
Yeah.
And then these other 2 are going to bond to an oxygen
Uh-huh.
as a double bond. And of course, my oxygen has
Oh,
1, 2, 3,
3,
4,
so.
5, 6.
Mm-hmm.
Okay. So that's my shape of this.
Mm-hmm.
Good here?
Yeah.
Okay. So now the question is how many, remember these, because I'm bonding these 2 things together, you know, I can't imagine them going off in other directions. They've got to be going in the same direction towards oxygen. They've got to be in this area. So this is one area of electron density. I just have 2 pairs tightly packed in there. Instead of so this becomes a unit of 1 instead of a unit of 2,
Okay.
or 2 units of 1. And then here's a unit, and then here's a unit. So this is 1, 2, 3.
Mm-hmm.
Whereas if I were doing methane, right, then it would be 1, 2, 3, 4.
Okay.
Okay.
Okay, so it's kind of triangular planar.
Yeah, exactly.
But like the no pairs electrons of the oxygen is not affect like the angles of the.
Oxygen's not my central atom here,
Okay.
so we don't even worry about the oxygen.
Oh, okay, that's what was I confused.
Fair enough. That's a good point. We're only worried about this central
Okay.
molecule or central atom.
So if I have in another molecule no pairs of electrons doesn't affect the structure.
Correct.
Okay.
Let's do this next one here. Okay. CNH.
Okay.
So how many regions do you have here?
3.
Well, these are stuck between these two, right? So
Mhm.
that's just one region.
Yeah.
And then here's my other, so I just have 2.
Okay.
Okay, so what shape is this going to be?
Linear.
It's going to be linear. All right. Where are we at? Write the Lewis structure. Count the number of regions of electron density, lone pairs and bonds around the central atom. Single, double, triple bonds count as one region of electron density. Identify the electron pair geometry based on the number of regions of electron density. So linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, etc. Use the number of lone pairs to determine the molecular structure. If more than one arrangement of lone pairs and chemical bonds is possible, choose the one that will minimize repulsions. And that's it. All right. Carbon dioxide, go.
Okay.
Tell me its shape.
Linear.
If you're just going to do it that fast, that's great. Why is it linear?
No, because it's just,
It's 2 double bonds.
yeah,
Yeah,
with
so they're just going to go like this, right?
double bonds with it.
Okay. All right, great. Less than the code. All right, yeah, you've already done, we've just already done so much of this. We did water. I didn't mean to do all their examples, but we did it. SF4, go. You're going to need the periodic table. Okay. Number of electrons in sulfur. Yeah, I didn't do that well, did I? Didn't do that well at all. Let me do that one again. Yeah. So my electron shape is, what's this shape called?
Trigonal bipyramidal.
Yeah, trigonal bipyramidal. What's my molecular shape? That I gotta erase this. Right? Now what's that shape called?
That's square polynomial.
I don't know the names. Just
Okay.
trigonal bipyramidal electron pair geometry to minimize lone pair. Let's Google it. Seesaw. Anyone seesaw? I couldn't remember which one.
That's new. Really.
It is new. We haven't talked about that yet. Yeah.
Yeah.
Yeah, definitely. So here's why it's called seesaw, I think. Yeah, I don't know. I think, you know how seesaw works. You got the thing, a bar going this way, and they're kind of at an angle. You know, it's, you know, there's a seesaw in there by somebody's imagination. It's been a while since I did that. That takes me back to being like 16. Last time I think I remember learning seesaw or having to do it. What time do we have? It's about to total, isn't it? All right. Let's do one last one. XEF4. Tell me how many valence shell electrons on that one, because I don't remember. Xenon. Oh my. I'm not playing around. Okay.
But it has 8.
Okay, so this is my deal, right? So I've got 1, 2, 3, 4, 5, 6 regions.
6 regions.
Octahedral.
6 regions should give me
Octahedral.
XE, and I'm going to get one going up, one going down, right? These are going to be my, these have to be my unbonded, right? By the rule that we had earlier. And then I've got to have my, is this any different than that?
It is. I think after you get rid of the 2 unbonded is going to be seesaw.
Oh, I've got 4. I'm sorry, I'm just treating this like I had 3 again. Like it's just not, something's wrong here. So F, 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 F. Okay, when I get rid of these 2 unbonded, that's going to be
They're planar
square
Square
planar. Yeah, I'm trying to say tetraplanar. Square planar is what it's going to be because we can play connect the dots, right? Okay. Good. Y'all are great.
Okay.
I will see you next week.
When?
We've seen each other once in 2 weeks. Oh, well.
What?
Oh, let me stop this and I'll answer your